Good morning and welcome back to our next episode of Chapter 6. Yesterday we learned about composition of functions. So you did adding, subtracting, multiplying, dividing, and composition. And today we are going to talk about an inverse function and what is an inverse function. So let's start with what an inverse relation is. Again, a relation is just a set of ordered pairs. So if I have the ordered pairs 1, 9, 3, 8, 5, 7, 7, 8, then the inverse of that simply swaps the domain and the range, the x and the y. So in an inverse, the domain and range swap. So if A is my relation, then the inverse relation would just be 1, 9, 8, 3, 5, 7, or 7, 5, and 7, 8 becomes 8, 7. So you literally just switch the x and the y. Two functions are inverses if and only if their compositions are the identity, which we'll get to later on in this section. And the symbol we use for inverse is f with a little -1 exponent. So we would say this is f inverse of x. So f of x, f inverse of x, and we use that little -1 to show that they're inverses. Now, if we have a relation and we want to find the inverse of the relation, again, it's very, very simple. If these are the points and this is the graph of my relation, then we simply have to switch the x and the y, literally just swap places for x and y. So the original had 2, 4, and my inverse has 4, 2. And then if we graph this, there's something about the graph I would like you to see. So green is the inverse, and we use the little apostrophe next to the letters. Again, we read this A prime, B prime, C prime to show that it's the image of A, B, and C. And a function or a relation and its inverse will always be reflections over the line y equals x. So if you look at A and A prime, you can see it's reflected. C and C prime, you can see the distance from this line is the same, and it's reflected over that line y equals x. And again, reflections over the line y equals x swap the x and the y always. When we have a function and we want to find the inverse, there's a few steps that we're going to use. So the first step is we'll replace f of x with y. Again, f of x and y are the same thing. We use f of x when we're talking about functions so we can identify which function it is. But then we said that an inverse swaps the domain and the range. So in this equation, we're going to, sorry, I don't have my stylus, so this is a little messy. We're going to swap x and y. That looks like an arrow pointing both ways, doesn't it? So x equals, my finger does not, this doesn't want to work with my finger today. Alright, let's try again. There we go. Okay, so x equals 3y plus 2. So we swap we replace f of x with y, and then we swap x and y. So they will switch spots, and then solve for y, and these are the steps you'll use every single time you're finding an inverse. Solve for y means get y by itself. So I want y alone. So I'm going to subtract 2 from both sides. And x minus 2 equals 3y. And then our last step will be divide by 3. So now y is by itself. And then our very last step is another notation change. We're going to replace y with our new inverse notation because this is now the inverse of the original function. So I can say f inverse of x equals x minus 2 over 3. And notice that my original function takes x and it multiplies it by 3 and it adds 2. While my inverse divides by 3 and subtracts 2. So an inverse function kind of undoes what the original function is. This one multiplies and adds, this one subtracts and divides. And again, these steps, write them down because you're going to be using them over and over again finding inverses. So then again, when I graph the function with its inverse, here's my original function in blue, here's my inverse function in green, and again, you can see that those two lines would be a reflection, if I could draw it straight, over the line y equals x. So those are our steps for finding inverse. We're going to talk a little bit in class about inverses where well, let's just think really quick for a second. Inverses with restricted domains, and I'm not a huge fan of this example here. But if you think about this original graph, x minus 7 squared, that is a parabola shifted to the right 7. Now, if I reflect this over the line y equals x, then, hold on one second. Okay, sorry, I got distracted by someone in my house. But if I take this point 7, 0, then the reflection of that point would be the point 0, 7. And this actually becomes this thing is so obnoxious. Okay, and then it's kind of hard to see. I'll try a different color here. This becomes the point for this graph. Again, it's kind of hard to see. I didn't draw it very well. But reflected will be like kind of like a parabola facing sideways. But is that graph in green that's so beautifully drawn, is that graph a function? And if you think about the vertical line test, hold on, let's see, okay, no, okay. The vertical line test, we can see that it's not a function. So in some cases, we will have to restrict the domain of the inverse for the inverse to be a function as well. And we will talk about that more in class with some examples, but just be aware that sometimes when I take something that is a function and I were to flip it over the line y equals x, if I'm just flipping the graph over, and even doing this algebraically, we get a inverse that's technically not a function. And so an inverse has to be a function as well, so we will have to restrict the domain in some cases. And again, we will discuss that one more in class. Now, let's see what else I want to do. Verifying inverses. If I have two functions and I want to show that two functions are inverses, then we are going to use composition. So we talked about that yesterday. F of g of x and g of f of x, if both of those, when I do both of these, equal just x, then these functions are inverses of each other. So let's look at an example. Excuse me. Offhand, just looking at this offhand, this function takes x and multiplies it by 7 and adds 4, and this one divides by 7 and subtracts 4. So they look like they could be inverses. But what we have to do is actually find the composition, f of g of x. And again, f of g of x means I'm going to replace this x with g of x. And that's what's done right here. So 7 and then g of x plus 4. The 7's will cancel out. X minus 4 plus 4 cancels out, and we are left with just the x right here. Now over here, g of f of x means I'm going to replace this x with f of x. So that's what's done here. That'll be 7x plus 4 minus 4 divided by 7. And again, when this is all simplified, what do we get? X. So when you compose a function with its inverse, because this one multiplies and adds and this one subtracts and divides, they essentially cancel each other out and you're left with just an x. So those two functions, when we compose them, kind of undo each other, and we have x in both cases. So we would have to do the composition both ways, f of g and g of f. But if those are both equal to x, then that is how we verify that they're inverses. So anytime it says you're given the two functions and you want to determine if they're inverses, we don't just swap x and y and get y by itself. But to verify or determine, you actually have to find both of these. And if they both equal x, then you have inverse functions. And I think that'll be enough for this video. So the key things are being able to find the inverse. The main thing that we're going to be looking at in this section is just finding the inverse with those 4 steps that I gave you, and also verifying. And I think that's where we will stop for today. So until next time, have a great... I hit the stop button before I was done. Have a great afternoon, evening, or whatever time it is that you're watching this, and I will see you soon.